Okay. So once again, I would like to welcome you to our 6th seminar today with Professor Rosaldo Rossetti from the University of Porto, from Portugal. He will give us a talk on artificial transportation systems as the basis for studying ITS, smart mobility and sustainable communities. And I will give you just a short bio of Professor Rossetti. So Professor Rossetti is an associate professor with the Department of Informatics Engineering and a senior research fellow with the Artificial Intelligence and Computer Science Lab at the University of Porto. He served as a member of the Board of Governors of the IEEE ITS Society during term 2011-2013, and was a member of the steering committee of the IEEE Smart Cities Initiative from 2013-2017. He's currently a co-chair of IEEE ITS Society's Artificial Transportation Systems and Simulation Technical Activities Subcommittee. His primary research interests include behavioral modeling, social simulation, and machine learning, with applications to the design of sustainable socio-technical systems. He's also a member of ACM, APIA, the Portuguese AI Society, and the European Social Simulation Association. Hi, Rosaldo. Thank you very much for accepting our invitation to come and give your talk here. Please, the floor is yours.
Thank you very much, Marin, for the introduction.
Okay, so here you see.
Do I need this?
Here, screen.
Buenas tardes.
Buenas tardes.
Good
Afternoon.
Perfecto.
Maybe it would be better in Portuguese or Spanish. Portuguese.
Okay, entende português? Okay.
In English is okay, sorry.
Okay.
So can you see the screen right now? We will just start.
Yeah, we are seeing the screen, only the screen. Yeah.
Okay, perfect. So we will share it now. Do you see now the title?
Yes. Yes.
Okay, thank you.
Okay. Good afternoon. Buenas tardes. Thank you very much, Marin, for the introduction again. A bit of a disclaimer before I start. So those of you that attended my presentation last year, I'm afraid you're not going to see much new during this presentation, but at least recalling some of the ideas will be good for us to motivate some discussion, I hope. Okay, so for today's seminar, I'm going to try and motivate the concept of artificial transportation systems as the basis for us to study social technical systems. And I would like to emphasize on 3 main concepts here: intelligence, smartness, and sustainability. So basically, these are the 3 pillars of the research I'm conducting now, and I plan to build a platform to help us analyze these 3 concepts in conjunction in an integrated basis, so that we can somehow be able to design better social technical systems. So the goals for today's seminar basically are 3. I'd like, as I said, to analyze ITS as a market mobility and sustainable community as a basis for us to get insights into how to implement support decision and policy making in these areas. And also, I would like to establish an understanding of artificial systems, and more specifically, artificial transportation systems, from both a methodological as well as an architectural perspective, so we can identify the modules that comprise these systems. And finally, I would like to explore the potential synergies and cross-fertilization opportunities between artificial transportation systems and intelligent systems, supported by multi-agent systems, artificial intelligence, as well as machine learning, and I would include also computer simulation. So I'll try to organize the presentation in 3 parts. First, we are going to talk about the basics of transportation, as transportation is generally studied in traditional methodologies. Then we are going to understand the concept of artificial systems, and more specifically, artificial transportation systems. And finally, I'm going to share with you a vision that we have in terms of how to organize all these concepts in an architecture underneath methodologies that can support decision-making and policy-making so as to improve social technical systems from new performance metrics such as sustainability, okay? So as for the transportation domain, generally, we usually consider these systems from this perspective of, or at least the performance of transportation systems are generally associated with congestion in general, okay? So indeed, the transportation is very important, both socially and economically speaking, because transportation moves people and moves goods as well, okay? And this photo was taken basically just when after or during the pandemic, we had a lot of constraints for mobility, and basically people were stuck at home, couldn't move. And we witnessed a huge improvement in terms of pollution. So the air was clean, so everything was fine, no cars on the roads. So that was an amazing time, okay? But just after, when the impositions or the constraints were alleviated, people started again moving crazily on the roads, okay? And this photo basically shows a picture of the inner ring in the city of Oporto in Portugal in a rush hour, as busy as the times before the pandemic. So this, once again, confirms the huge importance that transportation has in our lives. So how to tackle traffic congestion then? We basically have three ways of tackling congestion on road networks. We can implement physical modifications, meaning transportation networks are constrained by their capacity. So we can't actually put more and more vehicles on the road as we wish. We can only do that to the extent the network accepts new vehicles. And whenever we try to extend this capacity, we do that by adding new roads or extending new old roads with new lanes and so forth, okay? This is very expensive, very disruptive, and very dependent on public decision, on political decisions. We can also improve capacity by implementing intelligence in control systems, making the traffic lights more intelligent. And we have done so in a good way. So we have improved traffic control systems to the extent that today we see very easily intelligent traffic lights on the roads, but although they have been implemented in a proficient way, they cannot be considered as a lasting solution to this problem. And finally, we can do differently from the two first approaches. We can try to influence the behavior of the traveler, the driver. So this is very difficult because in the end, travelers are not like message packages in a computer network, okay? Because we send message packages on a computer network to wherever we want, they will obey us, okay? But when we are basically dealing with drivers and travelers, we cannot guarantee that drivers will accept the information we give to them even though the information conveys important data regarding the performance of their trips, okay? So we needed to be very convincing to those individuals on the network and to make them change their behavior. So dealing with the driver, the traveler, is a very, very challenging aspect in these solutions, okay? So transportation has been studied from this econometric perspective of demand on the one side and supply on the other side. On the demand side, we have people traveling, looking for transport solutions, transport services. On the supply side, we have road networks, control systems, public transport, and other services. So why do we need to study demand then? Because on the supply side, we can just plan it, design a new supply infrastructure, and implement it. But on the demand side, we need to study this because we needed to understand how to predict or forecast travel patterns. We needed to evaluate the transportation network performance in terms of how the network is being used by travelers and the drivers. And also we needed to plan and manage the growth of the urban areas. So although we control and manage the traffic infrastructure in short term, we needed to plan in long term how this will basically accommodate the growth of the population, okay? So in the end, we needed to understand the modeling requirements for us to understand demand. So we needed to understand the behavior of individuals, and then we needed to aggregate these individual behaviors into the level of traffic flows and volumes, so that this will affect the behavior of the network, okay? So basically, this is more or less the basics of the traditional transportation analysis framework. And transportation has a typical spatial structure. So everything happens in the space. So we have trips, journeys, travels happening from one origin to a destination on our network. So basically, those regions in the network that generate trips or attract the trips have many different characteristics, and they are divided into zones. So we have origin zones as well as destination zones. And we characterize those zones using many different variables, like a number of residents, some facilities the zones have, like parking areas, shopping centers. Shopping centers, for instance, attract very much trip on the network, and other socioeconomic characteristics of the residents, like what are the rich areas in the city, what are the poorest areas in the cities. So we needed to understand how this zoning strategy is basically implemented in each city we are analyzing. And then, of course, when people decide whether or not to make trips, if they do make a trip, they will do that throughout a network composed of links and nodes. So basically, we will have this graph structure, links and nodes, for each of the modes of transport we have. So generally, we have a graph for streets, allowing cars to move. Then we have a graph for the buses, basically allowing the bus services to be implemented. Then a graph for the trains, for the metro, for the taxis, for the pedestrians, and so forth. So we have a multi-layer structure with multiple graphs, and they are connected basically at the points where people can actually change the mode of transport while they are performing a trip on the network, okay? And the characteristics of this infrastructure will be those of the links and nodes. For instance, a link can be associated with the distance or with the time it takes to be traversed by a vehicle. And in the end, the performance of the trip is generally associated with the time taken to traverse a link in this network, okay? So all links traversed in my path from my origin to my destination will basically sum it up. The times will be associated with the performance of my journey. Of course, the generalized cost is no longer able to take into consideration new performance metrics as we see people concerned today, like pollution or footprint, carbon footprint, or preferences of tourists and so forth, okay? So we needed to have more rich cost functions to represent all the utilities that different people will have on their journeys, okay? Because one person basically can value itineraries that will have a garage or the schools of the kids. Others will basically privilege the itineraries where they can find touristic points. So the utility function should be implemented and conceived in a way that it is able to capture the different interpretation of utility for the different journeys, okay? So the traditional way of analyzing transportation systems imply making decisions in different levels. So we have 4 main dimensions in this decision-making process. One first dimension is to decide whether or not to make a trip. So this is related to choosing an origin, where to go. So this is related to choosing a destination, which means to take. Am I going to drive my own car? Am I going to take the public transport? Am I going to walk? So this is related to the mode. And then finally, I needed to select the itinerary. So this traditional process of making a decision while people are deciding or planning their trips is the so-called the 4-step model, in which we have 4 main components in this decision-making. One, which is basically related to trip generation, then the trip distribution, then model split, then trip assignment, each respectively associated with generating origins, destinations, modes, and routes. So basically, this is an iterative process, and when I am analyzing any aspect of the transportation system under study, I needed to go forth and back in this process, trying to calibrate the models and evaluate the results of my assessment. So this is basically the traditional methodology for us to analyze transportation. One question that is important to make at this point is whether or not this traditional approach is suitable for us to study new aspects of today's transportation systems. Because now we have, besides these different metrics, we also have different technologies. So autonomous driving will affect completely the way that routing, for instance, traffic assignment can be performed. So any other and other aspects will also influence the way these 4 modules in this traditional framework will be integrated, okay? Then, of course, we can analyze the trips in a single hour. For instance, the rush hour in the beginning of the day, or during noon, or during the end of the day. So when we are making this local analysis, we are talking about the the within-day dynamics. So we are basically analyzing one single leg in my itinerary. So am I going to one single destination, from one single origin to one single destination? But if we analyze multiple legs together, or even trips made regularly, day after day, then we have a loop, and we have the so-called day-to-day dynamics. And in this outer loop that you see in the figure, you can add a learning module. So basically, people repeatedly doing some journeys can learn with their journeys, and they will somehow assimilate the patterns they observe, and this learning process will make people more familiar to the network. And this, of course, will finally affect the way that people make decisions and decide on the itinerary they want to make, okay? So we can't actually deal with transportation system directly with the system, because that would be disruptive. So generally, we make a simulation model of the transportation system, and we analyze all the aspects we wanted to change in the system and the effect of these changes. We do that resorting to simulation tools. And basically, the simulation tools will be dependent on the granularity of the study we are performing. If we wanted to study vehicles interacting with each other, the way they accelerate or decelerate, or they change lanes, then we are talking about microscopic simulation, okay? Then if we are not interested at all in basically preserving the identity of each individual vehicles, we just wanted to know the aggregated flow on the roads, we are talking about macroscopic simulation. And in the between of the two approaches, we have the mesoscopic simulation, which deals with platoons. We are not actually looking into the way they interact within the platoon, but still we preserve the identity of each vehicle. So whether or not to choose between micro or macro or meso will very much depend on the computational power, and ultimately very much depends on the kind of study we are basically carrying out. So this is basically how we conduct studies in the transportation domain. Well, as we have witnessed through time, we, in the middle of the 80s, in the last century, we witnessed the emergence of the so-called intelligent transportation systems, the ITS. And when people started basically putting together all the pieces of technologies resorting to information and communication together, they realized the structure that service providers, the owner of the infrastructure, the cities, would be collecting data from huge sensor networks. And with this data, they could transform the data into useful information for the end user. And as you can see in this figure, you can very clearly see a pattern of a process on the data, transform this into useful information to the end user from the left to the right. Okay, so this was one-way communication only. So all the information that we started receiving in the middle of the 80s last century were produced by the providers, the service providers. So they were responsible for installing the sensor network, collecting data, transforming data, and basically conveying the information to the end user. So this will change and have changed recently. We are going to discuss this later on. But the main structure of this concept of intelligent transportation system is formed by multiple modules. And we can emphasize from the multiple modules at least 4 that are of interest, at least today. We have the so-called Advanced Traffic Management System, ATMS. So the figure you have on the top, on the right, are the traditional integrated control centers. So every city has a control center like that, okay? Even more centers if the city is huge, okay? So basically there, they have all the service providers and the authorities, the law enforcement people, basically observing, monitoring, and controlling, managing traffic in a short-term basis, okay? Then we have ATIS, so the so-called Advanced Travel Information Systems. Those are responsible for conveying information to the end user. So in the middle, we have the variable message signs we usually find on the motorways, telling us reduce speed to a certain value, or the time to certain destinations from this point on are 15 minutes, 7 minutes, 13 minutes. So we can decide whether or not to deviate from our original itinerary. And then finally, we have the advanced driver assistance systems on board, basically helping drivers to drive safer, like braking systems and so forth. And also the advanced vehicle control systems. So basically control systems that be in charge replacing the driver. So I would say that these 2 systems actually were the precursors of the autonomous driving that we see today, okay? So the vehicle are equipped with sensors, and now they are able to drive themselves without the influence of the drivers, okay? So this is a future that we can witness today already, okay? And this technology was ready by the beginning of the 2000s, but we are still facing some issues with law, because we never, one aspect of these systems is that who will be responsible if in case of an accident? Is the car, is the driver? So this is a very tricky issue, okay? And although the technology exists already, so we are still facing these issues that are to be overcome before we can actually have these systems operating on a daily basis in our systems, okay? So this is basically the infrastructure that we found in the former ITS system. And we have evolved to a different paradigm now, because people now, citizens, are aware of ICT. They know how to use ICT. They know how to access apps on the web and download them onto their mobiles and start using them. And more importantly, they are equipped with a mobile that is powerful enough to process heavy computational tasks on the top of your hand. So this is amazing, because this opens up a huge opportunity road ahead using this two-way communication for new business models. And we now witness the emergence of the so-called smart mobility. So the question is whether or not ITS is the same as smart mobility. If we translate these 2 terms into Portuguese and maybe into Spanish as well, so smart mobility could be translated by intelligent mobility and something like that, right? Very much like in Portuguese. Mobilidad inteligente. Mobilidad inteligente. Okay. Yeah. Okay, but in Portuguese at least, we translate it to mobilidade inteligente. So we are using intelligent to represent the smart part in this designation, okay? And this is not completely correct, okay? Because smartness has to do with the sense of opportunity rather than be completely intelligent, okay? An intelligent system is a system that does what it has to do correctly, flawless. At least they have been designed to behave like that, okay? A smart system, well, at least the way they are being implemented so far, they bring some opportunistic characteristics to the way they are being used. Because people are now using applications also trying to exploit the opportunities of earning some money from what they are using. So new business models are emerging. Not necessarily means they are correct in what they are doing. And some of those, as we are going to see, are being banned because then the regulator sees that, okay, this is completely wrong, this doesn't have any support by the law, so we need to adapt, okay? So smart mobility is a concept that still needs to be defined a bit better than what we can basically consider just to be an intelligent system, okay? So this is my point here. Okay? Smart mobility or smart systems are not the same as intelligent systems. So intelligent systems will try to implement things correctly. Then we have Waze, for instance. So it's very controversial, and it still is, because the people started using their private cars as a taxi-like mobility platform, okay? Then we have, this is Uber. People have been using their private cars as a taxi-like platform, selling their rides to people and earning money. Then we have ways in which people share the information, and the information shared by the Waze platform is even better than the information the owner of the infrastructure gets from the sensors they have installed 20 years ago, okay? So actually they are buying information from Waze to improve their traffic congestion predictions. So this is amazing, okay? Then we have this platform, although it is old, it is very nice to exemplify how people are profiting from this platform. So this monkey parking platform was implemented in San Francisco, California, to allow people to sell their parking places in public parking areas. So basically, when they were leaving their places, they broadcasted the information, selling the place, so who want to take this place here? And started receiving bids. Okay, wait me 5 minutes and I buy your place. No, wait me half an hour and I give you $100. So people started basically doing this auction-based market around public parking areas, okay? Of course, it was banned. So the regulator, as soon as they perceived all the new business model actually beneath this platform, the platform had to be banned from the market, okay? But although controversial, it is a very nice example of how people actually see utility in the applications they use. Then we have personal transportation as well. This is more related to the sense of joy. So people will use segways, scooters, bicycles, or even walk because they enjoy doing that, okay? So this is on the side of smart mobility. okay? So intelligent transportation systems try to do things correctly, well, looking into the system optimum. Smart mobility is basically oriented to the utility the end user is basically interpreting as they use these platforms. Then we have the Sustainable Development Goals suggested by the United Nations, and one of those, the 11th sustainable goal, is to make cities and human settlements inclusive, safe, resilient, and sustainable. So we now face the need to implement sustainable applications. So sustainability is very much related to preserving the resources that we share. So everyone actually wants to have his or her share of the resource, but we can't actually compete to the extent we are going to extinguish the resource. We need to preserve it. And how actually we do that, okay? So it is related to energy efficiency, sustainability of processes, optimal resource allocation, and so forth. So here, the citizen is central and should play a participative role in preserving the resource. So these are the three concepts we want to analyze and put together, okay? So we have intelligent systems, and in these cases, we have performances system-oriented, so we are trying to implement system optimum. We want to optimize the system as a whole. We have hard control, so basically it is the regulator and the operators that impose those metrics to the system. It is infrastructure-based, so regulators and operators will affect the infrastructure, and are usually based on the concepts related to critical systems. Okay, so everything is critical, timely on timely basis and safety basis, and all the characteristics of a complex system should be included here. Then we have a smart system. So differently from the previous, we have performances user-oriented. So performance is measured upon how actually people sense and perceive utility. This is based on soft control. We have a market-like infrastructure that actually will rule the way people will exchange their experiences, their data, and so forth. It is demand responsive because it looks at basically allowing people to have answers to their own demand, and service-oriented because basically a set of services will be oriented to meeting these demands that we may find in the population, okay? Then sustainable systems, differently from the two others, will have their performance oriented to the resource, how we preserve the resource. So control is expected to work on the concept of collective intelligence. So we expect that people reach consensus in preserving the resource because they are social aware of their behavior affecting the resources. And it implies community engagement for us to implement this, okay? If we put these three together, then we have accessibility in the end, okay? But analyzing two by two, so if we put intelligent transportation with smart mobility together, we have a market regulation. So the free market regulating smart mobility will be somehow affected by the regulators on the side of intelligent transportation. They will try to impose, like they are doing now for Uber, for instance. In the beginning, Uber was very controversial, okay? But then when taxi drivers started complaining, the regulator basically thought it was indeed very necessary to impose some regulatory basis for the Uber and other platforms like that to work in peace with traffic drivers, okay? But still today, Uber drivers now are complaining because they don't have the security and their employment like traffic drivers have. So this is the regulator basically managing this free market regulation that we find in smart mobility, okay? When we combine intelligent transportation systems with sustainable systems, we now have the intelligent systems favoring energy efficiency. So everything now is being oriented to preserving and being efficient in an energetic terms, okay? And then when we put sustainable communities with smart mobility, we have the agents of change. So what are the policies that will indeed make an influence, an impact on the way people make decisions so that they can orient their selfish behavior into a more social, aware behavior that will altogether favor sustainability in the whole system, okay? So if we put the three together, we have an answer for the accessibility problem in transportation, okay? Accessibility is not only a term used for people having access to a place, like installing ramps or other stuff like that, okay? Accessibility is also a matter of allowing people to be able to pay for their own fares for using public transport. So accessibility is very much related to societal issues like equality, equity, fairness, inclusion, and social justice. If we put these issues in all the three dimensions that we have discussed so far, then perhaps we can have here the basis for implementing sustainable communities in transportation systems, okay? So basically, this is the trichotomy that I would like to introduce. Then talking a bit more about the concept of artificial systems and why are these systems good for us to study the combination of the three first concepts that we have discussed so far, okay? So basically, this concept is not new. So in 2003, it was coined as artificial transportation systems, those that have the ability to integrate different transportation models and solutions in a virtual environment. So we are talking about a simulation environment, allowing us to test with and experimenting with new approaches to improve transportation without actually affecting the transportation in real world, okay? So the basis for artificial transportation systems borrows concepts from social sciences, artificial intelligence and machine learning, multi-agent systems, distributed computing, and virtual reality, okay? If we see this picture, we perhaps can identify some concepts that are being sold today as new concepts like digital twins. But in 2003, they idealized this structure in which we have, on the one hand, the natural system, and on the other hand, the artificial system, both basically running together, side by side, okay? One affecting the other, and the artificial system basically reflecting all the dynamics of the natural system. And with these systems running together, we can basically implement strategies for three main tasks: management and control. We can test before on the artificial system and implement after in the natural system. Experiments and evaluation. So we can evaluate whatever modifications we want to implement before we actually implement them in reality. Then, of course, we can use this as a platform for training technicians and other practitioners in the domain of transportation. So these two systems running together is the key for artificial transportation system, okay? And this idea very much resembles the one that we are now seeing in digital twins. So basically, the idea is more or less the same, okay? So with digital twins, we have a replica of the natural twin, and with the digital twin, we can test with different strategies, improve things, and then implement those back into the natural twin and so forth, okay? So basically, this is the idea. We have done some stuff in this area, combining different simulators to test with different problems. Like in this case, we have used IEEE HLA standard for simulation interoperability to combine a microscopic simulator with a simulation model of the powertrain of an electric bus. And basically, we had this very detailed model of the powertrain simulated in Simulink to analyze the performance of the battery while the bus basically moved over the network, interacting with other vehicles, braking, accelerating, and then we would this behavior of the bus affecting the performance of the battery. So this was a very nice work we implemented with the Caetano bus manufacturer in Portugal. And we have tested with real electric buses operating in the Frankfurt airport. So we got the data and we calibrated the model. And basically we demonstrated that the simple approach of having these two simulators working together were able to help us analyze this somehow complex setting. Then we also combined in another experiment 3 other simulators. One network simulator, so the OmniNet++, to test communication between computers in a communication network, okay? A agent-based platform, in this case JSON, implement the so-called belief, desire, and intention architecture. And then again, a microscopic traffic simulator. Basically, the idea here is to have agents, rational agents or deliberative agents implementing BDI to negotiate and somehow decide on the formation of platoons on the network in order to have vehicles basically navigating on the network together in platoon formation in order, for instance, to improve their efficiency in terms of fuel consumption, for instance, okay? If you have many trucks in a platoon navigating together, so the aerodynamics of this platoon will allow the trucks behind to save fuel as they navigate on the network, okay? But then they should be obliged to respect the leader, which imposes the speed and the route, okay? So basically, we put these 3 simulators together to test this kind of solutions. And we implemented an auction-based coordination to decide who would be leading the platoon. Basically, this was our approach in this project. And of course, with the increase of the size of the platoon, 5 minutes, okay, we would basically would lose in terms of the global utility of the platoon, which is expectable. But then we checked on the communication network simulator that for the platoon to reach a consensus, they would spend more or less 1.5 seconds to reach consensus, which is reasonable in a transportation setting, okay? which proves that this sort of strategy could well be implemented in reality, okay? So this is something that we basically verified in this. Well, as time is very short, I am basically jump this part, can I? You have the slides on your side, so we can check those, and perhaps if you have questions, you can ask me. I would like only to introduce this project, which was a European project in which we had all the actors on the road network being integrated in one single platform. So drivers, pedestrians, two-wheelers, and basically the idea is to analyze safety. We implemented the cockpits for people to actually use the system instead of basically being observed in reality to avoid accidents and so forth. And our team was responsible for modeling the pedestrians in this project, okay? So basically we resorted to information coming from multiple sources like sensors from the mobile application that we have installed in the control group that we had participating in this experiments. We also had the videos, the footages using smart glasses with a camera. So we would have first-person footage from the pedestrians. And with these footages, we had psychologists basically analyzing the footages and deciding on which aspects of the experience of the pedestrian should be basically investigated in more detail to have a cause effect for the decision-making process to be modeled in a more suitable and accurate way, okay? So we have implemented these pipelines to merge all this information and aggregate the data to make the final analysis, okay? So for the mobile platform, we had the accelerometer and the GPS, so we could basically track the pedestrian. And from the smart glasses, it is loading, yeah. We had this first view of the pedestrian, and with that, we could do also some measurements. And we also had the pedestrian using a virtual cockpit. So with the virtual glasses, doing some itinerary, and we could also basically evaluate the decision-making process of the pedestrian. So all this put together can help us build some models to interpret risk proneness of the pedestrian in different settings, okay? So this could be written by a decision tree like this one, okay? So how we plan to do this in a more practical way, okay? So let me just tell you about this structure here. We first envisaged this structure in which we had these two systems working together, the natural system and the virtual system. As you see on the right, the natural system with all the players, the actors, and then on the left, you have the multi-agent representation of what you see in reality, okay? But an addition that we made to this traditional approach was to implement a layer on top of the simulation model composed of expert systems that can observe what is happening in the artificial system and basically collaborate in order to come up with an integrated solution to whatever problem we try to solve in the transportation domain. Basically, we would have in this layer expert in different areas, an expert in public transport, an expert in traffic control systems, an expert in oh, it's missing the word, an expert in pollution or CO2 emission, and so forth, okay? So if our problem is with traffic control, of course, this expert will have a bigger weight in this combined solution. But in the end, we don't know if it is a linear combination of the solutions, because the agents will work together, will try to collaborate in order to come up with a solution that is best for the system as a whole. So this is the idea of this layer on top of the simulated model that we have there, okay? And we have basically joined forces with these laboratories. So LIAC is my lab, together with the CITA and CISTEC, which are research labs at the University of Porto. We joined forces to evolve that initial concept to a more elaborated infrastructure. And in this case, we believe that we can put all the concepts that we have discussed here in a way that this could be a possible platform to support decision-making in contemporary transportation systems, considering the 3 dimensions that we have discussed: the intelligence, the smartness, and the sustainability, okay? So on the bottom, we have the natural system together with the artificial system, okay? Both are basically feeding the system with data, okay? The natural system is feeding the system with naturalistic data. The artificial system is feeding the system with simulated data, okay? Artificial data. Then this data lake collects all the information and will basically work on this raw data into knowledge that will be used by our multi-agent decision support system. In the center of this green layer, you're seeing the picture in the picture, okay? To the right of this layer, we have machine learning as a service and simulation as a service analytical tools available to the agents to use in different situations. Of course, generalizing this is very hard. We could not at all generalize this in a way that the agent could interpret a problem from scratch and basically generate a formalization of the problem and apply those tools in order to analyze the situation and come up with a solution for that, okay? So that's why on the left side of this green layer, we have domain models. Basically, those are parametric pipelines of analytical processes that we need to check with experts in the different areas to pre-prepare those to receive or to be used in the decision-making process. And as those pipelines are selected for a certain analysis, so their modules will basically instantiate the appropriate analytical service on the right. So basically, this is how this layer here is expected to work, okay? And on the blue layer, on top of this architecture, we have an API that can be used by developers of apps, service providers, as well as researchers, okay? App providers and service providers will basically implement services that will affect the natural system. So this way, we can have this feedback loop closed with the natural system, okay? On the way to the right, we have basically researchers experimenting with new ideas on the artificial system, okay? So in this infrastructure, we basically are following the principles of artificial systems, and we are closing all the loops, and we expect to have here a platform that besides testing new stuff, we can also implement the solutions in reality through the app providers and service providers, okay? So basically, this is the idea. Of course, this is not easy. We have some challenges ahead. So coupling AI, machine learning, and simulation methods into analytical services is hard. So we have many challenges here, like interpretability and explainability of decision-making processes, meta-modeling and scenario setup automation. Here we want to implement the concept of agent-directed simulation, cause-effect triggers that will basically start emergent behaviors in multi-agent systems. And simulation as a service and machine learning as a service is also something that can be considered a hot topic at the moment, okay? Then we have on the behavior analysis side, some challenges like how we synthesize a simulated society or a demand, okay? So we need to understand activity-based models, discrete choice, how we perceive utility, so how we introduce these perceptions into our behavior models, and also concepts like social practices and social norms, how we integrate this into our framework, okay? Social coordination strategies, so strategies to align user equilibrium and system optimum through incentives, so closing the gap between user equilibrium and the system optimum. So what are the methodologies to study societal issues as well? So those are also big challenges ahead. Digital twins, so we have talked about this already. So methods for synthesizing a population in a digital twin. How actually we implement methodologies to verify, validate, and accredit these digital twins. Because this is not only a question of having a model of a population, this must be credible for the decision maker to be certain that what is being generated by this platform is acceptable for them to make good decisions and policies, okay? And then finally, test the impact of contemporary concepts that we have been seeing in most European calls for projects in European projects, like cooperative ITS, cooperative, connected and automated mobility, urban vehicle access regulation plans, shared mobility and mobility as a service, and electric mobility, okay? Those are also very nice challenges to study within the scope of this framework that we are implementing. So to wrap up this seminar, conclusions. So transportation systems are very rich in terms of problems. So they indeed motivate a lot of development in artificial intelligence and machine learning, simulation, multi-agent systems in different areas. And they can be considered complex social technical systems full of different challenges, okay? So the dimensions of intelligence, smartness, and sustainability is also the trichotomy that we want to explore within this framework, okay? And for us, the artificial systems, namely artificial transportation system, they can establish a platform for us to explore the mutual benefit and cross-fertilization between transportation and intelligent systems, okay? So I think this is a very rich area for you that want to decide or need to decide an area to work in your master's dissertations or PhD. So you're welcome to face these challenges and tackle one of those problems, okay? So I think that's it for the moment. Thank you very much, and sorry for taking too long.
Pablo, are there any questions? You can check. Yes. You have access to the people. So let me see. I will have 5 comments in the chat.
I can answer the first one. Buenas.
Yes, actually, they're just greetings. So there are no questions here. Okay, I will just accept Sasha if he's there.
He tried to connect at the beginning. He was waiting, Sasha was waiting.
But there's nobody there now. Okay, so I just see two participants in the.
So Sasha was lucky enough to miss the
Yeah,
seminar. So it means that I need to come again
and give another.
and
class, exactly,
repeat
exactly.
the
So
talk.
I have a question. So in the Dynacity, basically you showed the
Dynamicity.
Dynamicity, it showed the architecture which pretty much corresponds to the digital twins, right? It looks like an extension of a digital twin to the whole society, the whole transportation network, right? I mean, it might be connected how is it connected with digital twins?
Actually, to the best of my knowledge in this area, I haven't actually seen in the literature a vision as integrated as this one we are proposing, okay? Because digital twins are basically thought like a digital representation, separate digital representation of the natural systems. And most of the efforts we have been identifying in the literature, they don't even mention the need to run the digital twin in parallel with the natural system. It's just a replica of the natural system with which I'm going to test new stuff. And then if I have the possibility, I will try to implement my results in the natural twin. And the literature is not very clear about the natural and the digital twins integrated and running together. In my opinion, they should be, because twins grow together, okay? So metaphorically speaking, I understand like this. And that's why we basically implemented this notion of ACP, in which parallel means that the systems literally grow and evolve parallelly with each other over time. So answering your question, I don't think that is literally what people are doing out there in terms of digital twin. We believe that we are adding a bit more to the concept, at least hopefully, right?
We discussed in some of our group. So ideally, the digital twin should, as you said, grow together, and what you do in the digital twin should be reflected in the real world, right?
Not necessarily. They can, well, then we are in the side of analysis, right? Because whenever you trigger some modifications to the digital twin, it's more or less like you open a tiny branch from that point on. You have the digital twin still growing, but then a different instance growing in a different time branch, but actually reacting to your modifications, okay?
And they can be
yes.
multiple.
Yes, yeah, exactly. Then we have multiple branches out of different points in this analytical line. And this is important because you, with the different branches, you can check the deltas, the differences of what would be happening and what is happening with your modifications, and decide whether you're improving or not. So it's navigating in tiny branches from different points in this analytical timeline.
So in the sense that Alberto said, the digital twin can affect the physical twin, and the physical twin can affect the digital twin. It's a two-way street.
The natural twin Yes, but you still needed that the natural system or the physical twin is connected to the digital twin so that I can keep the correspondence of the two in this timeline, or at least in the main timeline of the digital twin.
So the digital twin is capable of foreseeing the future by doing what if then analysis.
Yes,
While the physical twin really is a little bit more myopic, just knowing the present.
yeah, exactly. In the digital twin, physical twin relationship, you have a natural time scale. But when you start experimenting with things with the digital twin, you can compress time. And then you can experiment with future aspects of the digital twin, which you couldn't do in the physical twin. So yes.
Yeah. Thank you very much. Are there any more questions in the hall or online?
But maybe you may know that we are in our group, we are now working. Maybe value awareness engineering, so related to ethics, and how to build systems and how to instill in the systems the notion of reasoning according to the human values of the either of the users or the community and so on. How do you see in your presentation, you presented, especially at the end, the core scenario, and I think it could be interesting to add explicitly some notion of human values.
El lunes los muchachos están viniendo y nos turnamos. Uno entra aquí a la reunión y los otros quedan afuera.
Some notion of this characteristic somewhere in your approach. I saw some pieces, especially in the end when you talked about society and the fairness or the equity and so on. I think it's important to have it when, for example, you talk about the system optimum and so on, there to have into account also that maybe when the system proposes a solution, for example, it will depend on who is the system proposing the solution to. And according to the values, we may want a solution that is efficient in terms of we want to get our trip back home and we want to arrive in the shorter time. For me, that would be my preferred value to have more free time, but maybe you prefer a solution that is more environmentally friendly or this kind of things.
Yeah, this is really a good point, and I think we could add this as the basis for the utility interpretation layer that I have mentioned, because how you interpret utility very much depends on how you value the outcome of your actions, or at least the expected value of your actions when you decide for one or another action. So this concept that you are mentioning and formalizing in your group could be the basis for this layer. As a matter of fact, I have a PhD student looking into this concept of yours of value-based analysis, yes.
We have a project on value engineering.
Many people working here.
Oh, okay.
They all work.
So, okay. So I hope you see some value here in this.
Evaluating things in the different manner. We have a heterogeneous system, each one will look at their value, key performance indicators.
Yeah, we needed to speak about this.
Thank you. Okay, so thank you very much, everyone. Thank you very much, Luis, Antonio. We will stop here and see you in the next class next week.
Muchas gracias.
Thank you, Rosaldo, for being again here, and hopefully see you also next time.
Once
Yes.
next time I will talk about difference.
Okay. Muchas gracias. Hasta luego.
Bueno, muchas gracias.
Gracias.